I'll be doing it more than one way, but at least this will be the first way that I'm going to unify. So section 15.9, change of variables in multiple integrals. So suppose, oh boy, suppose we have some region here. Let's say in the UV plane. Let's call this region S. And suppose I have some transformation, T, which transforms this region S into this region R in the XY plane. So suppose that UV is transformed by T to XY, and it's so nice that it also has an inverse transform that transforms R into S in the UV plane. So, change of variables. Suppose T is a C1 transformation whose Jacobian is non-zero. So we can have some invertibility. And that T maps S in the UV plane onto a region R in the XY plane. Suppose that F is continuous on R, that T is injective in the interior of S. Then we have the following. The integral of F over the region R is just the integral of F over the region S in the UV plane times the absolute value of the Jacobian. I think I gave you this notation. The Jacobian is just the matrix representation of the derivative. And so I gave you this notation. I usually use the J, but I gave this notation once or twice before. And now we're going to use it. That's what they use in the book. Okay, so another way to write this is that the triple integral. So now suppose instead of this going into 2 dimensions, suppose it goes into 3 dimensions. I'm not going to draw it. So the integral, triple integral of F over the region R is equal to the triple integral over S, where again, S is now in the UVW plane, UVW 3 space, where F has coordinates now we've changed the coordinates of UVW coordinate system times the absolute value of the Jacobian. So again, we have to multiply by the absolute value of the Jacobian. So when we were doing polar, let's say polar coordinates, if you actually take the Jacobian, the absolute value of the Jacobian, you get the value R. So that's why we multiply by R. If you take cylindrical coordinates and you look at the absolute value of the Jacobian, you get an R. If you look at spherical coordinates and you take the absolute value of the Jacobian, then you get a rho squared sine phi. So that's why we had to multiply by that strange additional factors. So the reason that we're having to multiply by those strange factors because it is the Jacobian. So we're really just multiplying by the Jacobian. Okay. Once we look at differential forms, it really all comes out to, just because it's a change of coordinates. And so you're just going in, it's just a change of coordinates formula. Okay. So let's do some examples. Oh, I didn't erase that. It doesn't really, okay, so. Page 1100. In exercises 15 through 20, use the given transformation to evaluate the integral. So I want to evaluate the integral, double integral, of x squared minus xy plus y squared, where R is a region bounded by the ellipse x squared minus xy plus y squared equaling 2. And the transformation is the following. X is equal to rad 2u minus rad 2/3 v. Y is equal to rad 2u plus rad 2/3 v. Okay, so let's do this. So first off, I guess, let's try to figure out what the, of course, it's the one above, what the Jacobian is. So let's try to figure out the Jacobian. And let's just get rid of this. And then add a page for what I just, oh, well, and get rid of that. Okay, so let's do this. So first off, let's figure out the Jacobian. So this is, and maybe let's, and maybe I'll do it in small notation. So x, u, the partial of x respect to u, partial of x, partial y respect to u, partial y respect to v. Okay. So let's figure out what each of these are. So the partial of x with respect to u. Okay, so, well, the partial of this is just rad 2. So the partial of x here with respect to u is just rad 2. Let's take the partial of x with respect to v. Well, it's just going to be rad 2 minus rad 2/3. Okay. Now let's try to find the partial of y with respect to u. Partial of y with respect to u is again another rad 2. Partial of y with respect to v is just going to be a positive rad 2/3. Okay, so let's calculate the determinant. Let's calculate this Jacobian. So I have that this is equal to I need more space. So I'm going to have a rad 2. Let's see, I have rad 2/3. Okay, I'm just trying to see how much space I need. And I have a rad 2 and a rad 2. Okay. Oh, and it's a minus there. Okay, so let's calculate this. So I get rad 2 times rad 2/3. So that's this equal to 2 over rad 3 plus 2 over rad 3. And so this is equal to 4 over rad 3. Now, of course, the absolute value is just going to be the same thing because it's positive. Okay, now let's look at this guy here. So let's see what this is. And so let's figure out what that is. So I have x squared minus xy plus y squared. You should notice that this looks very familiar, like what you did back in calculus, well, pre-calculus, and what you did back in calculus 2, doing a change of variables, a rotation of an axis, so that you can get rid of this bad sort of cross term here. So it should look very familiar to you guys, hopefully. So this is equal to x rad 2u minus rad 2/3 v minus, oh, this is going to be nice, rad 2u minus rad 2/3 v times rad 2 plus u plus rad 2/3 v, the product of the sum multiple of the product of the sum and difference of two terms, then plus rad 2 plus rad 2/3 v squared. So this is equal to 2u squared. Actually, I'll probably just do it this way. This is equal to 2u squared minus, oh, those aren't just nice. This is going to give you a 4 over rad 3 uv plus 2/3 v squared minus, this again, this is going to be the difference of squares. So minus 2u squared minus and minus become a plus 2/3 v squared. Plus, square this out. So this again will be a 2u squared, but it'll be a plus 4 over rad 3 uv plus 2/3 v squared. And so let's cancel some things. So these cancel. Don't care which one I cancel of those. And so I get 2u squared, 2/3 plus 2/3 plus 2/3 is 6/3 v squared. So it comes out nice. It just becomes u squared plus, well, 2u squared plus 2v squared. Okay. And so that's sort of nice. Notice the ellipse now becomes something much nicer. Becomes a circle. So now, the ellipse in the UV plane. Okay. So in UV coordinates. Okay. So the ellipse was x squared minus xy plus y squared equals 2. And so this became, well, in the UV plane, u squared plus 2v squared is 2. And so this is just a unit circle. So I've I've changed this ellipse into a unit circle, which makes everything much nicer. And so I have that the integral over this ellipse, x squared minus xy plus y squared, just becomes, well, now I want to integrate over the unit circle. So I don't know, that's a unit circle. The unit circle of, well, this, which is 2 u squared plus v squared, times what we calculated for the Jacobian, which was 4 over rad 3, du dv. Okay, so now I'm assume that I don't know polar coordinates, but I'm going to change this into, I'll do another change of variable to make this look a little nicer, polar coordinates. But I'll assume I don't know anything about polar coordinates because I want to do this in general, and then we'll be done. So that u equal r cosine theta, v equals r sine theta. Okay, let's look at the Jacobian. Oops. So partial u r theta r theta. So let's see what that is. Hopefully it comes out to r, because that's what we, that was our multiplying factor when we did a change of coordinates into polar coordinates. And so let's take the partial of u with respect to r. Okay, so partial u with respect to r is cosine theta. Partial of u with respect to theta is derivative of cosine is sine, so minus r sine theta, partial with respect to r, is sine theta, partial v with respect to theta, is r cosine theta. Okay, so let's determine this Jacobian. And this will be what we need to multiply by. Phi sine theta, cosine theta sine theta minus r cosine theta. So this is equal to r cosine squared theta minus minus become an r plus r sine squared theta. And so we get this magic factor of r. Okay, good, which is what we wanted. So therefore, this integral, and maybe I'll start with the original integral. So that integral so my integral over the ellipse is now equal to, I just want to integrate d r d theta. Okay. And so this is equal to 2 times 4 over rad 3 is 8. Oh, I don't need nearly that amount of space. 8 over rad 3 u squared plus v squared is r squared times the Jacobian, which was r, so this is an r cubed. Now, theta here, since we're going around, since u and v are going around the, well, x and y, we're going around the whole ellipse, then u and v have to go around the, have both plus and minus values. So theta has got to go from 0 to 2 pi, has to go all the way around. In this case, a circle corresponding that to that ellipse, so 0 to 2 pi. And while the radius turned out to just be a unit circle, so I'm integrating over this unit circle. And so the unit circle is just from 0 to 1. Oh, I forgot I wrote it here. So I'm integrating over the unit circle. So it's just integral from 0 to 1. Okay, so let's integrate this. So this is integral 0 to 2 pi of 1/4, so that's 2 over rad 3 r to the 4th from r equaling 0 to r equaling 1. And so this is equal to the integral 0 to 2 pi of 2 over rad 3 d theta. And so let's integrate this. And so if I integrate this, I just get 2 theta over rad 3 between 0 and 2 pi. And so lastly, I get This is equal to 4 pi over rad 3. And that is the value